So today we'll look at algorithm analysis. And before we begin, if you have any worries from our last lesson, if you have any challenges, can you please indicate? Somebody is saying that the last class was too long. Was it too long? Our lectures are supposed to be for how many hours? Delegate, we are supposed to have the lectures for how many hours? 2 hours, right?
Yes, 2 hours.
Then why is somebody complaining that it was long? Shifu. So normally it's supposed to be 2 hours. All right. So if there is no worry, we are going to go ahead. So today we'll look at algorithm analysis. We'll understand why there is need to analyze algorithms. We'll also look at algorithm complexity, specifically the space-time complexity of algorithms. We'll look at algorithm execution, time cases. Then we'll look at asymptotic notations of algorithms, okay? The big O notation, the omega notation, and the theta notation. Then we'll look at some common algorithms for greedy algorithms, divide and conquer algorithms, and dynamic programming. Okay. So now algorithm analysis. So you see, like we saw last time, we said an algorithm is simply a sequence of steps, a well-defined steps that are ambiguous, that are simple, that are computable for solving a particular problem. Okay, that is what an algorithm is. But you'll discover that after writing an algorithm, you will know that the algorithm needs to be executed on a computer system, which means it needs to use some computer resources like the processor. It needs to use also the memory. So what you need to do is you need to make sure that your algorithm is using these resources as optimum as possible. So that's what we mean by the efficiency of algorithm. So it means you need to ensure that your algorithm is efficient in terms of memory usage, in terms of processor time usage. Okay, because you can have a single algorithm, or you can have a single problem with maybe 5 algorithms. But when you look at these algorithms, you see that they do not have the same efficiency. One is taking too long to execute. Another one is occupying much memory time. But at the end of the day, you need to select an algorithm that is very efficient in terms of memory usage and in terms of processor time. So each time you write your algorithm, you need to first of all analyze the efficiency of such an algorithm, okay? And the efficiency of an algorithm can be analyzed first of all before implementation, and that is a kind of a theoretical approach. It means that you, after writing your algorithm, you are going to assume that all the factors are constant, for example, and then you try to compute the algorithm and estimate the processor speed and also the memory that the algorithm is going to use. So this one is a theoretical approach to estimating the efficiency of an algorithm, because you don't actually run the algorithm, but you imagine that you do a kind of a manual calculation. Okay, then we have the second approach, which means you will need to run the algorithm on a real environment. So the first approach is a priori approach. The second approach, a posterior analysis, where you need to implement the algorithm in a selected programming language, and then you execute that algorithm on a target computer. Okay, when you execute the algorithm on a target computer, you are then going to evaluate how much memory time it is taking, and how much how much memory space it is taking, and how much processor time that algorithm is taking. Okay, so this one is a kind of an empirical analysis, because you do it on a real environment, on a real environment because the algorithm is implemented on a selected programming language, okay? Unlike the first approach that is more of theoretical because you do a manual calculation. So these are the two approaches that you can use in determining your algorithm's efficiency. So you don't just write an algorithm and you jump to implementing or to deploying it to production, but you need to first of all ensure that this algorithm is actually very efficient. It is not consuming too much memory. It is not taking too much time to run to completion. Okay. Now, what is the need? What is the need for analyzing algorithms? That's a big question. What do you think is the need for analyzing algorithms? We need to analyze algorithms. Why? Because to solve a particular problem, this is a simple scenario is taken here that maybe you want to go from a city A to city B. You might take, there might be about 5 or 10 routes that are leading to that destination. But now all the routes are not the same. One might be longer than the other. One might be, there might be traps on the other road. There might be, you see, they do not have the same, I want to say the same, you don't need the same effort to arrive at the destination B through the different routes. Maybe if two people are working at the same, or if you have 5 persons working on the separate routes and working at the same speed and using the same resources, you will discover that one of the persons will arrive before the other, and you see something like that. So that's why there is need for you to analyze your algorithm to ensure that you are actually using the optimum, you are optimizing the usage of resources. You are optimizing the usage of resources because you know algorithms run on a computer infrastructure where you have the hardware, you have the software, and in the hardware you have essentially the memory, you have the processor, and these resources are costly. So you always ensure that you optimize the usage of these resources in your algorithm, okay, by selecting the most optimum path to arrive at the solution. Okay, so the goal of analyzing an algorithm, now we're looking at what are the goals of algorithm analysis. The goal of analyzing algorithm is to be able to compare algorithms, mainly in terms of the running time and also in terms of memory usage. Okay, you can also compare the algorithm in terms of developers' effort. Okay, maybe to implement the algorithm, the programmer needs maybe 10 days to write this algorithm, but another programmer with another algorithm, the programmer needs just 2 days. So you see that the effort that is required from the developer cannot also be neglected with algorithms. There are some algorithms that you will struggle before you arrive at, but there are others that are easy to get to the solution. So basically, you need to compare algorithms in terms of the running time. When we talk of the running time, we mean the processor. And we need to compare algorithms also in terms of memory usage and also the effort that is required by the developer. All right. Now we have what we call running time analysis. You know, when you have an algorithm, right? When you have an algorithm, you might start an algorithm, maybe like we saw last time, an algorithm needs input, it needs some processing, and at the end there is output. Okay, you can begin executing an algorithm and the input size is maybe 5. Okay, but as the algorithm continues, you will see that the input size is going to increase or is going to change. Okay, so the running time analysis entails like to look at how the processing time increases in terms of the size of the input. So how does the change in the input of the algorithm affect the processing time of that algorithm? It could be logarithmically, it could be exponentially, It means that if you have, for example, an algorithm that is starting with n variables, maybe n is 2, for example, what is going to, and the algorithm is executing at maybe using maybe 2 milliseconds in the processor. How is that algorithm going to behave when the input will be maybe 1 million, when n will be 1 million? How is that algorithm going to respond? How is the usage of the memory and the processor going to change as in relation to the changes in the input of the algorithm? So that is the running time analysis. So which is also very important, because when you look at your algorithm, you look at the beginning with few inputs. How is the algorithm running? What is the running time? And as the input is changing, how is it affecting the running time of the algorithm? So that is running time analysis. So you can have some inputs, like for example, the size of an array. If you start executing an algorithm with an array of size maybe 10, the algorithm will be executed. The algorithm will take a particular time to execute. What will happen when the size of this array will be 100? You will discover that the processing time will also change. Okay, but now how is the processing time changing with the size of the input? It could be changing linearly. It could be changing linearly, like, or it could be changing exponentially, or it could be changing quadratically. Okay, so you need to determine this, how your input is varying with how your input or how your processing time is varying with the size of the input. And we take an example of the size of an array. You can have the polynomial degree, for example. If you have an algorithm with an input which is a polynomial of power 4, okay, it is using a particular, or executing for a particular time. Now, what will happen when the polynomial will be of power 5 or power 6? You see that there is something that is going to change in the execution time of the algorithm. You can also have the number of elements in the matrix, starting with a matrix, maybe a 2 by 2 matrix. What will happen with the algorithm when the matrix will be 3 by 3 or 4 by 4 or something like that? So these are things that you need to consider. You don't just look at an algorithm running with maybe two variables at the input. Maybe the size of the input is 2, and then you conclude that when the size of the input will be 1,000, the algorithm will run the same, or it will be linearly. You need to estimate this and see that your resources or your available resources are going to be able to support this algorithm. Okay, this is also important in the acquisition of the resources that you will use in the execution of your algorithm. Maybe you want to command a particular processor type, particular memory, a particular graphics card. You need to, or graphics memory, you need to know what are the expectations of this algorithm. Okay, and you need to do this analysis, and with the runtime analysis as well. Okay, so now I hope there's no challenge at that level. You can always leave a comment. You can leave a comment as a chat, and I will look at this. Somebody is saying they cannot see my screen. Hosea, can you see my screen now? Hello? Hello? Okay, if you have any challenge, you just leave a comment, you just leave a chat. And delegate, please take note of the attendance.
Okay, sir.
All right, so now we'll look at algorithm complexity. Algorithm complexity. We have understood the need for the analysis of an algorithm. Every algorithm that we write, we need to analyze it. And when you're analyzing, you need to focus basically on the time and also on the space. Okay, so algorithm complexity is about, you have basically two factors that you use in order to decide the efficiency of an algorithm. In order to determine the efficiency of an algorithm, you have two major factors, which are the time factor and you have the space factor. Okay, and when we talk about the time factor, we are looking at the number of operations, which is more of the processor time. And when you look at the space factor, it is more of the memory size of your algorithm. Okay, just a minute. Let me. Okay, sorry about that. So in algorithm complexity, we have two major factors that we need to consider. We have the time factor and we have the space. Okay, and when we talk about the time, we are looking at the processor time. When we talk about the space, we are looking at the memory size, or the size of the memory that your algorithm will need. Okay, so they say that the complexity of an algorithm f of n gives the running time and or the storage space required by the algorithm in terms of n as the size of the input data. Right, so it is clear, it is giving the running time and also the storage that is required by the algorithm to run to completion. All right. So now we need to look at the space complexity. Space complexity. So the space complexity represents what? It represents the amount of memory space that's required by the algorithm in its life cycle. Okay, it represents the amount of memory space that is required by the algorithm throughout its life cycle. And in the space complexity, you are looking at the fixed part and you are looking at the variable part. Okay, you are looking at the fixed part and you are looking at the variable part. It means when we talk about space complexity, we are looking at how much memory, what is the memory size that your algorithm is going to need when it will run to completion. Okay, is it going to, for it to run to completion, is it going to take use 2 gigabytes of memory? Is it going to be needing 5 gigabytes of memory? Is it going to be needing just 3 megabytes? What is the amount of memory that will be required for your algorithm to run to completion? That is the space complexity. And here we have the fixed part. You know, when you define your algorithm, you have some variables that are constant, that do not change. Okay, so these variables will represent the fixed part of your space complexity. For example, if you have a constant like pi,
orange screen. Everyone get online class.
so pi will always be 22/7, no matter what happens. Okay, so this is a fixed part. Now for the variable part, you have some variables that are going to change as the execution of the algorithm is being executed. The content of these variables is going to change. So this is the variable part of algorithm. And for you to have the space complexity, you are going to take that constant or that fixed part plus the variable part of the algorithm. That will give you the space complexity of the algorithm. Somebody saying they didn't understand time factor. Okay, I think when we explain the time factor, you understand. So we said there are two factors. We have space and we have time. When we talk about the time, we are looking at how much time the processor is going to take in order to execute the algorithm to completion. Okay, that's what we mean by the time factor. There are some algorithms that the processor will run it for will take just 2 milliseconds and take it to completion. There are some algorithms that the processor will take 2 minutes. There are algorithms that the processor will take 5 minutes. There are some algorithms that the processor will take even 1 year to run to completion. Okay, you need to determine that. That is the time factor of algorithm. How much time will be required by the processor? How much processor time the algorithm will need to run to completion? Okay, and the time factor, if you take, for example, you consider that the execution time for an instruction is constant, okay, and that you have a kind of you have maybe n instructions to execute, then for you to determine the total number of total amount of time that will be needed, you just take the total number of instructions and you multiply by the number of and you multiply by the time that each instruction is taking. Okay, that will give you the time complexity of your algorithm. Okay, so it means if you have an algorithm that is made up of maybe n instructions, that is made up of n instructions. N can be 1,000, it can be 100, it can be 2, it can be 1. If your algorithm is made up of n instructions and the processor takes maybe c seconds or c milliseconds to execute one instruction, you are going to assume that your time complexity of your algorithm is going to be the c, which is the amount of time needed to execute a single instructions times the number of instructions that you have in the algorithm. So that is in an ideal case. Okay. All right. So now we have execution time cases. Execution time cases of algorithms. And in execution time cases, we have three. We have basically three time cases. We have what we call the worst case. We have the worst case, we have the average case, and we have the best case. Okay, from their names, it is basically the names already explain what they mean. That is to say that if you have the worst case scenario of an algorithm, or if you want to determine the worst case execution time of an algorithm, you are going to look at the highest time, okay, or the maximum time that that algorithm can ever take at a given value. For example, if you want to say the algorithm needs with n inputs, the algorithm can take a maximum of 10 seconds. It can never take more than 10 seconds. So it means this is the worst case scenario of that algorithm, when the algorithm is taking the maximum time that it can take. Okay, it means that you can have an algorithm that can take 5 seconds, 2 seconds, 3 seconds, 10 seconds. But in this situation, you are looking at the maximum time, the maximum execution time that that algorithm is going to take in order to run to completion. That is the worst case. The algorithm can never take time longer than what you determine as the worst case. So the worst case will always be at the top. Then we have the average case. The average case from the name is the average execution time of the operation of the algorithm, maybe implementing a particular data structure, like the average time. It means with the average case, you are going to determine maybe the worst case, and you determine also the lower case. Okay, so the average case is looking at the average execution time of that algorithm. And then we have the best case. The best case now is a scenario that is depicting, for example, the least possible execution time of that algorithm. Okay, the least possible time. If we take, for example, if we take an example of, let me try to do something. If you take an example of an array A, if you take an example of array A that is with this content, maybe we have content 2, 3, 84, 7, 9, 10, 11, 12, 78, 98, 9, sorry, there, 67. For example, if you have an algorithm like this one, okay, if you have an array as such, an array A, an array of integers with these values, if you want to look at, if you take, for example, a kind of a linear search algorithm, if you are asked to, if you want to find, if you are searching for, maybe search for 67, okay, if you are searching for 67 using a linear search, what is going to happen? The algorithm is going to verify all these elements. Okay, it is going to check the first element, is it 65? No. It is going to take the second element, is it 65? No. The third element, it is going to verify like that, and you will discover that the algorithm will be at the end, okay, will be at the end of it before it will discover 67. And the worst case will even be if the number that you are looking for does not even exist. For example, if you are searching for 70, if you are searching for 70, what is going to happen? Your algorithm is going to go progressively. It will take the first element, examine. If it is 70, it is going to display it is not 70. It will continue like that for all the elements. And your algorithm will take the pains of going through all the elements in the array and not finding 70. Okay, that is the worst case. It means that your algorithm is going to, this is going to indicate the worst case scenario of your algorithm, because it will run through the end and it will not even find anything. Okay, so it means that it is actually the worst case. Take, for example, if you are searching for 2, if your algorithm is to search for the number 2, what is going to happen? If you are searching for 2, as the algorithm is initiating the search, it's going to find 2. And that is the first thing that the algorithm can do. It must enter the loop, and looking here, it finds 2. And it means this algorithm will run at its best case, because it is the least execution that it can happen. The least number of instructions are executed, just one search, and it finds 2. Okay, so it means that the search for 2 in this case will be a kind of a best case scenario for this algorithm. Then if you want to look at an average case, an average scenario, if you search, for example, an element that is found at the middle of that algorithm, let me say 11. Let's consider 11 is at the middle. If you are searching for 11, what is going to happen is that initially your algorithm knows that it needs to count this as the size of the array. Okay, but now 11 is at the middle of the array. It means your algorithm is going to go halfway and it will discover 11 and it will end execution. So this is a kind of more of an average execution for this algorithm, because normally it was supposed to run through all this, but it did just half of it, for example. So you can consider these as being examples of situations that that describe the worst case, searching for an element that does not even exist, the best case. So this is more of a worst case. And this is more of a best case, because the element is found at the first position, and this is more of an average case, because the algorithm runs just halfway and it finds what it's looking for. Okay, I believe our meeting is going to end in some 2 minutes, so we'll come back. All right, we'll come back with the same link after it ends. Okay.